mood. I think it's a little over grandiose for the topic today. But as always, we're going to be talking about the laws of the universe, and so so we need to have something stirring to get our blood flowing to do that. Welcome everybody to Bite of Physics number 94. This is the 94th, I guess, in a series that we've been doing now for a couple of years in the Scientific Discourse House on various topics in physics and also in chemistry with Sam Tomasovi, my co-house guy, on accessible topics in physics that we go into in a little more mathematical rigor than you'll normally see, but not so much as to make them unaccessible, hopefully. And in particular, I think today's is a nice accessible one. It has to do with a little experiment I did last Monday floating on a lake in Maine. And I thought, oh, I should just do this because I'm still working on my musical harmony bite, which will come one of these days, but it's summertime and I'm running all over the place and I keep running out of time beforehand. So anyway, thanks for everybody for being here. As always, if anybody wants to be on the stage, hang out, you're welcome. This is not an exclusive club. Raise your hand and I'll bring you up, or Andy Hero or Shamash will bring you up. Shamash in either his guise as Shamash or in his alter ego guise as Logic Guy. But anyway, at the moment, we've got... Oh, wait a minute. Let's see. What did I just do? Oh, okay. Okay. I'm just screwing up. I got my club deck. I haven't used club deck for a couple of weeks, and I'm having to remind myself. Shamash, thank you very much for reminding me that I didn't have the music playing because I was muted. And how are you doing this morning?
Not at all. Thank you for hosting the room. And how are you? I hope you had fun with your vacation. I'm all right. I'm just eager to learn more physics.
Yeah, that's good. And I'm eager to learn more. I'll end today with a question. This has to do with a phenomenon that I've seen a lot, and I can't really find anybody who just in a very direct form addresses this phenomenon. I think it's got to be out there somewhere, but I'm having a very hard time getting somebody to just say directly what's going on. So we'll get to that. There'll be a little bit of a mystery at the very end today. Welcome, Andy. Thanks for being there. Hope I get to see you next week. Andy and I have been...
Just very quickly, we're live on YouTube for people to know, and you can catch this episode and previous episodes on the Scientific Discourse channel. You can find the link in chat.
Thanks so much for that, Shamash. And I always forget to give. I don't always forget to give the plug, but I will not today for your Philosophy Wednesdays, which was a particularly strident one. I got into some really pretty interesting things there at the end this time. So maybe people looking for drama on Clubhouse should know that Philosophy Wednesdays is a place to look for some of it. Anyway.
Yeah. I mean, you got to do what you got to do. We got to eat bread here. Come on.
But anyway, once again, Andy, I'm hoping that I'll get a chance to see you. We've been passing each other in the night for a couple of years now, and I'm on my way to my summer camp in Mendocino next week, so I'll be passing Andy a couple times. Anyway, good to see you here, Andy. Take care.
Yeah, that would be super cool. On your way down, I think is the opportunity. Mm-hmm. So I just want to say, Shamash, I really enjoyed that room the other day too. I thought it turned into a bit of a public therapy session or something, but it was fun to witness. And I thought you did a really good job. And I thought Ben eventually did a really good job too. Like it was great.
It was difficult, but thank you. I appreciate it.
And of course, as always, the perennial thorn in everybody's side, a guy who takes pleasure in doing it and takes pleasure in being kind of called out and noted for his ability to be a thorn in everybody's side. Benjamin!
With a hard R. Honest.
All right. So good. So let's get started. As I say, go ahead and raise your hand if you'd like to hang out on stage. You can ask questions in the chat. I don't necessarily see them. Sometimes Shamash will call my attention, or somebody else will, and that's fine. But the best way to make a comment or ask a question is probably to come on stage. So do so if you care to. Go ahead and open the slides. You'll see that today's topic is on lake horizons. This was inspired when I was floating. I floated several times out in front of the house that we were staying in on Kezar Lake in Maine. And it's a beautiful lake. It's a beautiful long lake. And sometimes it's a very calm lake, especially in the mornings before the ski boats get out and stir up the water. So I've got some pictures to show you from that. Interesting horizon things. So that's what we're talking about today. And if you go to slide 2 in the presentations, link to up at there at the top, just a few questions, kind of to start out. And I guess I always hesitate kind of to say it directly. This whole thing is inspired, I guess, by my encounters with people who believe that the Earth is flat, and I'm convinced that at least some of them genuinely believe that the Earth is flat. And part of the reason they do is that they don't see how water could possibly be curved. I think most of us might also be a little surprised thinking about, wow, curved water is kind of weird. But at the same time, I think most of us appreciate, I'll just answer the first question for us, is the surface of the ocean level? Well, I guess that's really the question. Is it level? I think we all know it's not flat. I think we all know that. But is it level? And then, and rather than actually asking for answers in sequence, I'll put them out there, and then I'll just ask for discussion if there is any. I think most people would say, if they thought about it for a while, well, yeah, it's level, but that's weird because I know it's not flat somehow. Is the surface of a lake level? That's a lot easier, right? You look at a lake and probably say, yeah, it's level, right? And you might even say it's flat. You wouldn't be far wrong, of course. But at any rate, it kind of begs the question, is there a difference between level and flat? And then is the surface of a glass of water level? So I've got those 3 questions. Are all those surfaces level? And then finally, to really put a fine point on the real thing that I'm after here, are any of those surfaces flat? So I'll just kind of put all those questions out there, and probably most of you know kind of where I'm going with all of this. But if there's any comments or questions or anything else about the implications of all that, now's the time. Oh, and welcome, Ben. To see you.
Hey, buddy.
Well, I think to answer that question, you have to introduce the concept of a level curve, and then that immediately introduces the idea that a level line could something could be curved and level at the same time, and that sort of like points out the difference between the word flat and the word level. So yeah, I think water can be level, or at least water is always approaching levelness, or because water is always dynamic too, to some extent. So
Now let
that's
me just
part of
ask,
the.
hold on just a second. So you said approaching levelness. Did you mean approaching flatness, or did you mean approaching levelness?
Oh, I meant approaching levelness, but
Okay.
like I would say, yeah, water is level, but it's more interesting than that, or it's a little more complicated than that. Part of it is that the concept of a level curve is actually gets kind of complicated when you start thinking about it. Like we've talked about geoids before, and it's like what would level mean? Well, like okay, so a level curve could be parallel to the sphere of the Earth, except the Earth's not a sphere; it's an ellipsoid. Except it's not an ellipsoid; it's actually kind of undulating. So you keep making these little exceptions, and whatever undulating curve you arrive at, yeah, you can be level to that.
Okay, good. Well, that's all nice commentary leading into the next slide, which we'll get to in a moment. If anybody else has comments
We
here.
haven't heard any answers though. He just like,
Yeah,
oh, there's this curvy thing with the mathematics thing. I haven't heard any answers.
that's right. I think I tried to give little hints at the answer. We'll get to that more. But this is exactly the discussion I want. Go ahead, Benjamin.
So you need a definition for level to begin with, which I think is just that the surface is perpendicular to the direction of a plumb bob where you hold it.
I love that.
But the most challenging claim that you're going to make is that if you were an astronaut and you went to Saturn and you were to stand on the ring of Saturn, you would be level. And your friend standing on the other side of the ring of Saturn, with his feet touching your feet, would be level.
Yeah, I'm not sure you need to go as far as the ring. You can just talk about a tiny little asteroid, right? Just standing on either side of a of an asteroid. Level, well, what level means, but you do stand. To stand, when you stand, of course, you basically have to make sure that your center of mass is above a point between your feet so that you don't fall over. Because if you lean so far that your center of mass is outside that, you do fall over. But of course, all of that invokes gravity, right? You can't talk about any of this without having something about gravity. And I loved the fact that you invoked the plumb bob, because that's exactly to the point, right? A level surface is going to be perpendicular to a plumb bob. And of course, that brings in a geometric concept that some people are maybe not completely familiar with or completely comfortable with, the idea of a plane, or at least a small piece of a plane that is perpendicular to a line. What does it mean for a plane to be perpendicular to a line? It means that every line that lies in that plane is perpendicular to the line. And then so you kind of, conjure up some visualization skills. This is where the book Measurement that Andy's been touting and that Ben has been touting and that all three of us have been reading or listening to recently, is kind of good at making the distinction between the real world and the mathematical world. But when we invoke the idea of perpendicularity of a plane being perpendicular to a line, we're not dealing with the real world. We're dealing with a mathematical world that the real world only approaches to some kind of an approximation. Anyway, I'm getting a little off the point here. Maybe we should move on to slide 3. Any last comments here before we do? Because we will answer some questions now. Okay, well let's do that. So this is really to answer the questions and to really get to at this point of, does water, it's commonly said, water seeks its own level. And of course what that means at some level is that the surface, at some level, that means that the surface of the water is itself level. If it's not level, the water will seek to make it level. If the surface of a calm body of water were higher, whatever that means, we have to think about that a little bit, at one point than it is at a nearby point, then water would flow until that's no longer the case, right? If you have water that's higher over here than it is at one point than it is just at a point nearby, then water will flow over to that point nearby until when everything evens out, when the kind of the sloshing stops, it is at the same height. Every point on that surface will be at the same height, whatever that means, right? And gravity is implicated both in determining which point is higher in the first place. If it weren't for gravity, you wouldn't even be talking about something being higher. What would that even mean without gravity? But also in making the water flow to correct that imbalance. It's the gravitational force that makes the water flow in order to eliminate one point being higher than another. So it's easy sometimes to forget how critically important gravity is, and we even sometimes can marvel. If you don't think about it for a moment, you can even marvel at the fact, wow, why is gravity always in the downward direction? I'll just kind of leave that one out there as something, because some people will hear that sentence and have to think for a moment. Wow, that is kind of weird, right? Why is gravity always in the downward direction? But this really gets the final thing here is to really get at the point of what we mean by level, to give the definition that Benjamin was hungry for. A level path or a surface, that is to say, a two-dimensional thing or a three-dimensional, or if you want a two or a three-dimensional thing or a one or two-dimensional thing, if we're talking about a path, a level path is a path such that at every point on that path, a tangent line drawn to the path at that point will be perpendicular to down. And so I show a path, a curved path that is level. It's level because at every point on that path, down is perpendicular to the path. And when I say perpendicular to the path, that's just shorthand for saying perpendicular to a, quote, tangent line, unquote, drawn at the point that I'm interested in talking about. Level surface is the same idea, except that now we talk about tangent planes. We talk about a flat plane that is drawn to be tangent to the surface. And we say that without defining it. We can define a little better what we mean by tangent, if anybody needs to. Maybe we should. But I've shown you an example there. So there's a surface that has bumps on it. It's not flat, but it is level because at every point on that surface, the surface is perpendicular to down. And to really put a fine point on that, if I were to place a ball at any point on that surface, it would stay there because gravity would be forcing it directly into the surface. There'd be no component of gravity trying to make it roll. There are no lower places on that surface. That's the thing that may be hard to wrap your minds around at first, right? There, you look at that surface, you say, well, it's got bumps, it's got high points and low points. No, it doesn't. It's a level surface. Every point on that surface is at the same height, if you want, as any other. Now, maybe people might take some issue with some of those words, but I'll stop there, see if there's any comments.
How do we find down?
Yeah, that's right. How do you find down? Well, the Benjamin already mentioned the most obvious way: just hang a weight from a string and hold it and see what direction the string goes. Right.
But that wouldn't work if you are on a level path, right? Because nothing would happen.
If you're on say again.
If you're on a level surface and you're trying to use that plumb bob, what I understood from what you're saying is that these arrows that you drew, this is the direction of the plumb bob, right?
Right.
Well, they're either all over the place, or I need an explanation for why moving to another place down would change.
Oh, okay. Well, I mean, I think you do know that if you were to come visit me in Los Angeles, down would be in a different direction, right?
Yes, of course. But what I would expect is to have all those arrows converging to the center of the Earth if this is where I'm defining down to be. Because a plumb bob would, yeah.
Okay, so
disregarding the fact that we are rotating and it would be a little bit, tilted.
Okay.
Disregarding that fact. But they should all converge, right?
Well, I understand why you might think that, and I was hoping to at least tweak you with the rotation, with the effective rotation, with the fact that down, there's almost no, I guess there probably is some place on Earth where down is toward the center of the Earth, but then I'm not sure I know even what the center of the Earth means. So mathematically, if we if we talk mathematically, it's not even clear what the center of the Earth is. So what direction is down? Up, down's the direction of the gravitational force, and the gravitational force can be altered if you have a big mass concentration. This is why, as Andy was talking about, why the so-called geoid. A geoid is a level surface, and it's bumpy as hell because down is not doesn't converge down at different places on the Earth. There's no common point that all downs head toward, even if you were to eliminate rotation and the effects of centrifugal force. But I think you probably know that. But just to say that, maybe if there's a follow up, does that all make sense?
I'm just wondering because I'm looking at your arrows and they're very different, and so
Right.
yeah, like I'm imagining trying to define down in that way. So there you have a plumb bob and you're walking, and then if this is really the direction, so if you look at that thing, the level path, right? The way this is drawn to me sounds like you have drawn a perpendicular to every tangent, which is always the case. Like you would never find a normal direction that is not perpendicular to the tangent. This is by definition. And so I'm trying to imagine, okay, how am I going
What
to
would make
abuse
that
that now
happen,
to
right?
lose that flatness or that, sorry, the levelness of the surface?
Well, so I'm not completely sure. I think at some point, of course, I would answer you by saying, well, I've exaggerated things here, right? On Earth, down does do this. It just doesn't do it as much as I'm showing. There are mass concentrations under the Earth. There are places like in the Indian Ocean in particular is a place where there's a big, I can't remember if it's a mass concentration or a mass unconcentration, but gravity is very weird, relative to the rest of the Earth in the Indian Ocean region. And so the geoid does a big dip right there in order to stay perpendicular to down, which varies pretty quickly, relatively speaking, in that area. Not as much as once again, what I'm showing here, of course, is an exaggeration. But it can happen on the Earth. I mean, it does happen. The down doesn't point toward a common point at different places on the Earth. So maybe I just leave it at that. If I just plead guilty to having exaggerated things, does that satisfy you?
No, I get it. Yeah.
Yeah, because I did. I definitely exaggerated things. Okay, so let's see. Let's move on to slide 4 then, and talk about horizons over spherical surfaces. Now, this may seem kind of unrelated, but I do want to be clear about, first of all, the whole level surfaces, first of all. Now I want to talk about a spherical surface, not necessarily water or anything else, not even necessarily a level surface, right? I'm just talking about the phenomenon of optical horizons on strictly spherical, in the mathematical sense, surfaces, whether or not they're level or anything else. This is kind of a completely separate topic here. And so I want to just suppose for a moment that we have light traveling in straight lines. Some of you know that light doesn't do that because of refraction and the fact that refraction changes at different places in the atmosphere. But if we neglect that for the moment and just talk about light traveling in a straight line in the area above a spherical surface, then in that case, two observers on that surface whose eyes are at those points A and B that I've shown there will just be able to see each other's eyes if the line of sight from one to the other, a straight line drawn from one eye to the other, grazes the surface of that sphere at a specific place that is, in fact, what we call the horizon for both observers, right? For both observers, that line of sight grazes the Earth at their horizon. Each of them has a different horizon, but that point is at the horizon for both of them. Let me just stop there for a moment, see if I've said anything there that calls into question anything. Okay. Okay, good. So,
I'm just wondering
yeah,
why
go
A
ahead.
is shorter than B, but go ahead.
Yeah, so I made A. Okay, good. That's a good question. And of course, you can see that it certainly can be. I did it on purpose. I didn't want them to be the same height above the surface, but I should have pointed out that they are at different heights above the surface. They are at heights above. If they weren't at heights above the surface, they wouldn't be able to see each other. Right? Anything that's on the surface can't see anything else that's on the surface because it will be below that thing's horizon if you think about that in a mathematical sense. So I do want to talk about observers whose eyes are not glued to the surface, but that are at some height above it. So I've shown A is at height little h above the surface. B is at height capital H above the surface. And then there's the line of sight grazes the surface at a distance little d from A, and it grazes the surface at a distance capital D from B. So if I just deploy the Pythagorean theorem as I've done down below for point A at first, I just write out what the Pythagorean theorem says. This is a spherical surface, so all of those, I didn't show the whole way to the center, but all of those go to the center of the Earth. Let's say this sphere is the Earth. Let's say the Earth is spherical. And let's say that it has a radius of 3,960 miles or 6,370 kilometers, which is pretty much what it is. Then the Pythagorean theorem, there are two right triangles there. I'm sorry if I didn't show them, but you can extend all those radiuses to the center of the perfectly spherical Earth and see that you get two right triangles formed on either side of the horizon. So let's take the one on the left, the one that applies to point A. One of the sides has length r, one of the sides has length d, and the hypotenuse has length r plus h. So if I simply apply the Pythagorean theorem to that, you see I can just get r squared plus d squared equals r plus h squared. I expand that square and I get r squared plus 2rh plus h squared. You can do that multiplication if you want, see that yourself. And the nice thing about that is the really big term, r squared is the really big term there. That completely cancels away. So I'm left at the second step with d squared equals 2rh plus h squared. And the nice thing now is that even I've gotten rid of the really big thing on both sides, the r squared. That's way bigger than d squared. So I've gotten rid of it completely, mathematically eliminated it. Now I have d squared, which is a pretty big thing, maybe, I don't know, is equal to 2 times r times h. Well, r is big, but h is presumably pretty small. So that makes it a mid-sized thing itself. And then I'm adding to that h squared. Now, if you think about h squared, that's h times h, and you want to compare that to h times 2r. Well, generally, 2r is going to be way bigger than h. So that h squared is really small compared to 2rh. And I expect that I'm not going to make too much of a mistake if I just take that equation and say that it says that d squared is very approximately, not very approximately, but very close to, but approximately 2rh. And then if I did that same thing, of course, for the other right triangle, I'd get the same thing. I'd get capital D squared is 2r capital H. For each of those. And that's I use that formula all the time. That's a really nice formula relating distance to the horizon to the radius of the Earth and the height of the observer. A lot of people, you may have heard 8 inches per square mile. If you've hung around with flat earthers at all, that's a thing you use. And that's basically what this equation is saying with some specific units put in. But I find it's just generally simpler to just use d squared equals 2rh. And I remember that. It's easily memorable because notice that you've always got that distance to the horizon, the height above the surface, and the radius. And those three things are typically very different in size. H is small, R is big, and D is somewhere in between. So it's easy to remember the formula because it says that if you square the mid-sized thing, the D, you get twice the big thing times the small thing. And that is literally the way I remember it. The mid-sized thing squared is equal to twice the big thing times the small thing. It's literally the way I remember that equation. Makes it really easy to quickly get the kinds of calculations that we're going to do in a moment. So any comments on that? All right.
Can I ask an annoying question? Because I get that a lot. I want just 30 seconds, and I want to get your feedback here. Why would you not say R plus H squared is basically R from the beginning? Like, why would you expand it and then cheat only with H squared? Cheat with the entire thing, right?
Yeah, well, so the problem with that, of course, is that I can try that, and what I then find is that D is equal to 0, right? If I just say, well, R plus H is basically...
Yeah, but because this shows that your entire math is mistaken, right? You got to stick to you know what I mean? Like all this approximation business, you see what you're doing here. You're cheating. And the Earth is really flat. You got to admit.
No, you're right. And in fact, I just realized that in answer to your question, of course, I didn't actually finish this slide. So thank you for asking it.
All right.
I gave an example there. Suppose H is 10 miles. 10 miles. Very few of us, I would wager to say none of us have ever been, well, I don't know, Ben might have been above 10. Have you been above 10 miles, Ben? I don't know if Ben's with us.
Not a lot, no.
What's
but you
that
have
in kilometers so that we know?
But you have been
16
in a
kilometers
plane,
something?
huh? Have you been in a plane at 10 miles?
I
more
don't.
than 10 miles?
Altimeters don't read in miles. Give me just a second.
16 kilometers.
Yeah, they don't read in kilometers
16,000
either.
meters.
They don't read in meters
53,000
either.
feet.
Yeah.
Okay, thank you, Andy.
Have you been over 50,000 feet?
No, I have not been over 50,000. I think the highest I've ever seen on an altimeter is 48,000 something.
Right. So even Ben, who trained to be an astronaut, has never been
Didn't
10
quite train
miles
to be an
high.
astronaut. I nearly trained to be an astronaut.
Nearly trained to be
I
an
was
astronaut.
headhunted as an astronaut, but didn't get that far because of a dodgy.
I didn't know they had astronaut headhunters.
Well, neither did I. It was a very fucking weird story, but it's not for now while you're in the middle of telling people about it.
Okay, well, some other time then. At any rate, so none of us, it turns out, probably, maybe somebody, if anybody down there has ever been above 10 miles, raise your hand, come up on stage and tell us about it. If you were that high, you get a distance to the horizon of 281.4 miles to be ridiculously precise. If I didn't make that approximation, I don't have to make that approximation. I can calculate D by taking 2RH and adding H squared and then taking the square root, like Shamash would have us do because he's concerned about this approximation. And if I do that from a height that none of us have ever been to, the value for the horizon is actually bigger than the one we get with the approximate by 0.2 miles, by 2,000 feet. Right, that's the distance to the horizon is approximately 281.4 miles. It's exactly 281.6 miles. So that's just kind of that doesn't prove that the approximation I made there is valid, but it's just to show you just how valid it is. And then I would point out that as H gets smaller, the approximation I'm making only gets better. And we're going to be talking in a moment here about heights of 1 inch, calculating the distance to the horizon when your eye is 1 inch above the surface. That's one of the things we're going to talk about when we get to the lake here. So, it's a good point. And this is a thing that I remember, I think all physics majors, math majors are concerned about, well, why do you get to make the approximation there? Why didn't you do it at some other point? And it's always a little hard to answer that, even though you can do as I did and show you that if you make that approximation in the first step, that r squared is approximately the same as r plus h squared, and I just say, okay, well, let's just throw them both out. You end up with d squared equals 0, which proves immediately that that was a bad approximation because d is clearly not 0. So yeah, anyway, thanks for asking that question, Shamash.
No, thank you, man. No problem. You're sweet. You're a
Okay.
sweet man.
So let's move on to 5. So here's what I did. I risked my iPhone for science. Just last Monday, I was floating on Lake Kezar in Maine. On Golden Pond, I listened to loons. I heard my first loon. Loons are both beautiful birds and they have amazing calls. So that's quite something. But I was also floating out on the lake and I just noticed I had a pool noodle under my arms just kind of support me so I could just kind of sit there. And I noticed there was a beach in the distance. And when I kind of paddled a little bit and tried to get my head up high above the water, I could clearly see this beach. But when I then brought my nose underwater and my eyes an inch or two above the water, the beach was not visible. It disappeared. And I thought, oh, this is cool. This is the lake curving. This is me having a horizon that's very close to my eyes and a beach that's 1.4 miles away that is now below my horizon for my eyes. So I thought, well, I need to document this. So I paddled back over to the dock, got my iPhone, and risked my iPhone. Without the pool noodles, I could not have performed this experiment. This is for Benjamin. This is the kind of things we do for science, Benjamin. And we often don't like show our data or our methods. But I'm telling you right now, this is the way I did this. I put the pool noodle under my arms. I held the phone kind of up there. It was hard lifting the phone because I had the pool noodle kind of in the way, but I could still lift it up to what I estimated was about 14 inches above the surface of the water. And then I could lower it. If I put the phone in the right orientation, and I did, I could get that lens about 1 inch, maybe even less, but something like 1 inch above the surface of the water. And these two pictures are taken, one about 14 inches above the surface, one at 1 inch above the surface. And you'll notice a couple things. The most obvious thing, maybe, I don't know if it's the most obvious thing, but I think it is that the beach is not, you don't see the beach in the second shot. It's clearly not visible and presumably below the horizon, but I'll leave you to decide that. But the more obvious thing is it's clear that the phone was higher in the first shot because the dock, I'm kind of floating out there right next to the dock that I was swimming off of, moves up by perspective. I've framed those two to try to keep the little hut. There's a little hut over just to the right of center frame, and I tried to keep that hut in the same place in both pictures. So that's, and you can see I didn't take the pictures in quite the same place. I had moved over a little bit to the left when I took the second picture. But it's just the luck of the draw there. I didn't plan it out well enough. So there's those pictures, and also, if you're interested, I made a YouTube both from those shots above, as well as some video clips. I have some video clips of the camera going up and down, and a ski boat coming toward me in one of them while I'm going up and down. And it's just kind of fun to watch the horizon, watch that beach disappear as the phone comes down. In fact, when the phone is just above the surface, you can see all the little bugs on the surface kind of jumping around. You can see that the phone is just about to go under the surface. So you can take a look at that if you'd like to later on. Okay, so any comments on that before we move on? Let's wait for a moment.
How do we know that you weren't paid to fake these pictures
Well, you
and
don't
put them here as real data? Like,
see this is
how do we know that?
well.
Were
See,
those Were those pool noodles properly calibrated?
Were the
Oh
what?
yes,
I
that's an
I want
important
to.
question.
Yeah, I want to see your pool noodle calibration certificate.
Oh, yeah, right. Actually, I have to say this was a massive pool noodle too. It was a really big one. I really enjoyed it. I thought about kicking my way across the lake. It was only about a quarter mile across the lake. I didn't do that because there were boats running by and things. But anyway, if I'd had more time, I would have gotten around to it.
Does your wife have any photos of you doing this?
Oh, I have. I put a photo. I put a video on my Facebook page. I took a selfie while I was using my feet to whirl around 360 degrees, and then claimed that that was another experiment that I did in conservation of angular momentum. But I was there. I was lying. You see, I will say in answer to Shamash's first question, the only reason I have for you to actually believe me is the integrity that I've established. Through a lifetime of being scrupulously honest about things, and then joking about things and making it clear that I'm joking about things. But I'm not really kidding about that, right? That is unfortunately all you have in science is your integrity. And if you lose your integrity, as Benjamin's quick to point out, you've kind of lost your integrity. That's a hard thing. Fortunately, it doesn't happen to most scientists, despite what Benjamin thinks. But it does happen from time to time. Anyway, thanks for asking. I know you were kidding at some levels, Shamash, but it is a good point I think to make. All you have is your integrity. Okay. So that's that. Let's move on to 6. So let's do these calculations for the Lake Kezar thing. Let's let H be 1 inch and 14 inches rather than 10 miles. If H is 1 inch, which is 0.0000158 miles, to get it into simple, that's what I usually do. I convert everything to miles, and then I use 3,960 miles in the formula. And I find that the distance to my horizon, when my eye is 1 inch, when the camera lens is 1 inch above the water, is 0.35 miles, 1,870 feet. The horizon is much closer to my eye than the beach, which is 1.4 miles away. And therefore, if you look at that diagram, you kind of see let point A be my eye, 1 inch above the horizon is 2,000 feet away, more or less. And then another, 1.2 miles or something beyond that lies the beach. And some of it's hidden. An amount capital H of that beach would be hidden, assuming that there's no refraction, that the light is traveling in a straight line, that the reason the beach is disappearing is because of the fact that the Earth is a sphere, all of those things, which you can decide yourself whether you think that's true. And I'll give you some reasons to think it's not in a moment. Okay, so if that's what for 1 inch. If the height is 14 inches, when my camera was 14 inches, then with the same radius, etc., I find that the distance to my horizon is 1.33 miles. That's about the distance to the beach. So that's what's just kind of convenient. I did not fudge those numbers. I estimated the 14 inches before I calculated the distance to the horizon. And I just thought it was interesting that distance to the horizon with 14 inches turns out to be about the distance to the beach. So that's once again, that may or may not be really where the horizon was. It only is if you believe light travels in straight lines, there's no refraction, the Earth's a perfect sphere, and that this is really why we have a horizon. You have to believe all those things, and you may or may not. And I will give you reasons to think that some of them aren't true. So, but we can also determine how much of the beach should be visible simply by finding capital H. So first we find capital D, that would be the distance to the beach, minus the distance from my eye to the horizon point, which we share with the beach. And then, having done that, I find out that the distance capital D is about 1.05 miles. Then solve for capital H. So and this is where my mnemonic comes in handy. I think, first of all, okay, capital H, that's the mid-sized thing. So what I have to do is I have to square the small, so I have to square the Sorry, no. Capital H is the small thing, so I need to square the mid-sized thing and divide by twice the big thing. Sorry, I really screwed that up. I talked about how well I remember it, and then I screw it up. I'm trying to find the small thing, capital H. So I have to square the mid-sized thing and divide by twice the big thing. And so I 1.05 miles squared divided by twice 3,960 miles. I find out that capital H is 0.00014 miles, or about 9 inches. So if all of this is true, if light travels in straight lines, if everything's happening the way I said it here, I would say that I am obscuring 9 inches worth of that beach behind the horizon. Now, do I really think that that beach is only 9 inches above lake level? Most beaches kind of come up 2 or 3 feet maybe. Now, I don't know much about that beach. I tried to look at Google Earth and see how high it gets above lake level. And I got some indication that it might be 2 or 3 feet above lake level. So there's a little bit of a discrepancy there. At any rate, there's certainly no debating the fact that the beach wasn't visible from 1 inch, whatever that means. And we'll talk about that a little more. So I think that's it. So that is a question, though. Do we think that looks, if you look at that picture on slide 5, there's a lot of beach there. It's hard to imagine it's really just 9 inches, even though it clearly does. Whatever it is, it clearly goes away when I have the 1 inch altitude picture. So any comments on that before we move on to 7? We're getting pretty close to the end here. I just want to talk about complications, couple complications, and then end. So first complication, confounding detail, and this is not really very important, but it is important to just talk about the fact that it is a confounding detail. There is atmosphere in the Earth, and that atmosphere gets denser as you approach the ground. And because it gets denser, light travels more and more slowly. Light travels more slowly through air than it does in a vacuum. And the denser the air is, the slower it goes. The slower it goes, the higher the so-called index of refraction. The index of refraction is just the ratio of the speed of light in a vacuum to the speed of light through the medium. So as the speed of light gets smaller and smaller, the index of refraction goes up, and that's what happens in the standard atmosphere. And that turns out, for reasons I'll talk about in a moment, to make light bend toward the Earth. And under standard conditions near the surface of the Earth, horizontally directed light curves with a radius. The radius of curvature of a light beam is about 6 or 7 times the radius of the Earth. That is to say, it doesn't bend so fast that it keeps up with that it just goes around the Earth, but it does bend toward the Earth. And that means, as the diagram there that I stole from a radar site, this is talking about refraction in radar, but it's the same phenomenon. Radar is an electromagnetic wave like light, does the same kind of things, even though the indexes of refraction may be a little different. And you can see there that the fact that light bends toward the Earth means if you follow those rays backward, the direction the light's actually traveling, the radar horizon is beyond the so-called geometric horizon, or the horizon in the absence of refraction. You could actually see a point on the surface of the Earth that's a little further away than you would be able to see if light traveled in a straight line. And of course, you can also see things that are above that, things that would ordinarily be blocked behind the horizon if light curves. So that actually allows you to see things, both things that are slightly below the point where they would be obscured otherwise, and also things that are slightly further away on the surface. That turns out just not to be a very big deal. It modifies that what did I say, 8 inches, whatever I said, 9 inches, modifies that maybe to 7 or 8 inches. I not as much of the beach is obscured. It also moves the horizon out to really even closer to the beach than I had indicated. I can see a little further. It makes my 1 inch horizon about 2,000 feet rather than 1,800 feet. But none of that really changes anything very much. And of course, it still remains the case that the beach does disappear when I go from 14 inches down to 1 inch. So we do have to somehow explain that, even if we can't get it precisely to the second decimal place. So, any comments on that one before? I think that's not a very big deal, but I'll pause for 5 seconds. So let's move on then to the bigger deal. Another confounding detail is something that you may not have noticed if you didn't look at that picture very closely. And this is a confounding detail that I've seen a lot when I do pictures of the horizon, especially with a zoom lens. There's almost always, when I take pictures of a horizon over a water surface, there's almost always this thin little, what's called an inferior mirage. And I've blown up the picture of the beach there so that hopefully you can see it. There's a little white roofed thing over toward the left that is mirrored down below. And other features are mirrored too, but most of them are shadows. I've drawn a red line at the place where, at least an approximate place where the mirroring happens. There's an inverted image of things above that red line, below that red line. And that's what's called an inferior mirage. It's the thing that makes hot pavement look wet, because you're actually seeing light from the sky that comes down to the surface and then refracts upward toward your eye, making the pavement itself look wet. What you're really just seeing is an image of the sky, but it makes the pavement look wet. This is a little different though, because it's very narrow. It's in my experience, it's almost always present when you look at a horizon over water, but you can't generally see it with your eyes because it's a very small little strip like this. And this was certainly no exception. There certainly was that imaging. If you look at the video I made, you'll see it as I move the camera up and down. You'll kind of see how the miraging makes things look not quite as clear cut as you'd like them to look. Now that miraging, that inferior miraging, actually replaces what would have been water with that image. That red line, presumably something like where that red line is actually where the water level is. But this light from those objects is coming down toward it and refracting up toward our eye so that we see it down below where the water would be, as indicated in that little diagram. If you check out that diagram at the top right, you'll see it's a radically exaggerated image of how these inferior mirages are formed by light coming into our eye as if it was coming from a much lower direction, with higher things appearing proportionally lower. I'm giving you the kind of the mirroring effect of the inferior mirage. Inferior mirages are really complicated by the details of the refraction profile. But this is I just want to say, this is a really common feature. And I have heard very few people comment specifically on this very narrow inferior mirage thing that happens at the horizon above water surface. If anybody has a good reference on it, I'm looking for it. I've spent some time looking, not exhaustively, but enough that I would have expected it to show up much more commonly than it does. And I'm just surprised that it seems not to have been commented on. So let me just do the last slide, and then we'll open it for discussion. Just to kind of show you how this miraging thing works. it's really about. I'm showing you there what are called wave fronts. These are places along. If you imagine a light uh, coming along, at first all heading downward. That wave front is what's called a locus of constant phase. And that as that wave moves forward, if you think about a literal wave approaching a beach, say, this is a wave, it's perpendicular to the propagation direction, but because the wave is moving faster at lower altitude than it is at higher altitude, the wave front a little further to the right now is slanted a little bit less. It's starting to approach perpendicularity to the surface, which it does in the third or fourth wavefront that I've shown there. And because the propagation direction is perpendicular to the wavefront, you see how the propagation direction then gets shifted upward. It curves upward into the eye so that the eye is tricked into thinking the light is coming from below the water. That's seeing that image, those images of the beach where there really should be water. We're seeing the images of the beach instead. So I just wanted to kind of show that because people rarely really talk about the mechanism of the bending in terms of these wave fronts. You don't see as much of that as you just see the bending of the direction of propagation. So anyway, so what causes that mirage, as I say there, in a nutshell, I'm just really not sure. These inferior mirages are always the result of an inversion near the surface. This is not the direction light generally bends in the atmosphere. It generally bends toward the Earth, not away from the Earth. Inferior mirages are always the result of an inversion below which the index of refraction decreases rather than increasing as it usually does. And it leads to faster light, right? Or I should say the faster light leads to the increase in the decrease, sorry, in the index of refraction. But that very narrow inferior image just above the apparent horizon over water is a surprisingly common phenomenon. I almost always see that when I take zoomed pictures of things like oil platforms or anything on boats, anything on the distance. You'll see this inverted image, and you'll see it in lots of pictures if you look at them. But it does generally require cameras with zoom lenses. It's just too small, too narrow a thing to really see with the unaided eye. And my largely uninformed conjecture is that it may have to do with humidity, the fact that the air just above the surface of the water is humid, which will generally decrease the index of refraction because humid air is less dense than not humid air. Light travels faster, all other things being equal, through humid air than it does through unhumid air. So that could be the reason. But humidity, when you have humidity and evaporation, you also have weird temperature effects that accompany that. Not completely clear what the full story is. The details are hazy to me, and I would appreciate any help if anybody knows anything about that. And with that, I'm done. We can talk about this or related things.
Well, I'm glad you brought this up because I've noticed this too. By the way, I'm driving, so I haven't really been able to look at your slides, but I think I know exactly what you're talking about because we both have Nikon P cameras, so we've seen the same things. And so first of all, did you happen to take temperature measurements of the water in the air when you did this?
I didn't, but I do know that I was told, and I believe because I was swimming and I'm pretty well calibrated for swimming in water, I was told that the lake temperature was about 75. That seems right to me.
Oh, that's warm.
It was pretty warm. I was surprised how warm it was. And the air temperature was on that same order. So it was a situation where there shouldn't have been any huge thermal kinds of things going on. But of course, the air itself is pretty humid in Maine, more humid than I'm used to, although it wasn't horrendous. So no, I don't have any good measurements, but I will say that I think the water temperature and air temperature were pretty similar. Don't think there
Well,
was any big
I
difference.
have I have always tried to take photos on days where the and for me this means kind of a cold day where the water or the air temperature is at least as close to the water temperature as possible. But I've always imagined so I too have noticed that like you can't get away from this. It's always there. And humidity, I mean, that might be a thing, but I also feel like you see this when if you take a photo down like on the floor, like on a basketball court, or you find some flat, or the coin trick on
Uh,
on a table, like on that it might just be like a millimeter, but when you get really close to like a glancing surface, I feel like you always see this a little bit if you look closely enough. It's kind of like it seems inescapable, and I've imagined it two ways. I've imagined it uh, like a boundary layer in the air. Like there's always a boundary layer, even if there's a lot of breeze or wind over, like the wind over the wing. There's always this little tiny boundary layer down there where the air is essentially stationary. And I think what that would mean is that there's just a difference in behavior that can be very small that might change like the temperature profile, like really close to the
just like
surface, the gradient
convection or
departs.
something.
Yeah. So, but that would also require a temperature difference. The other thing I've often wondered about, and I think I've asked you about this before, but I don't think I worded it very well, was that is there an effect, not refraction, maybe something more like diffraction? Diffraction is always described as when light or a wave passes an opening or something like that, but can a very parallel ray or like light over a glancing surface over a long distance that has a curvature to it, is there like something like diffraction happening, like a waveguide effect or something like that? Is that a possibility? I don't know how else to
Yeah,
describe that.
yeah. I don't know. I mean, I know what you're talking about, and I don't know really. I mean, just over a level surface, I wouldn't expect diffraction to really be a thing. Diffraction is caused by sharp edges, typically edges anyway, literally blocking light, and then these wave fronts kind of wrapping around behind. It's not about speed of. You can have an absolutely constant index of refraction. You'll still have diffraction just due to the fact that you don't get the Huygens wavelets adding up to the same wavefront beyond. You only have contributions from the part of the light that wasn't wasn't blocked. Anyway, it really is about edges, and I don't know quite how you'd get that, in a situation like this. But I won't rule it out. I mean, it may be that there's some kind of a diffraction-like effect going on.
Well, when I say it, it sounds dumb, but then again, I see like there are antennas that use like a waveguide kind of a thing. They, I think, use like a horn antenna, and that's using a curved surface to change the direction of an
Impedance
electromagnetic
matching or
ray,
something.
which is
Yeah.
what light is. So it doesn't seem that crazy, but I think I'm using the wrong words though. I don't know if there's a word for this.
Yeah. I don't know about, yeah, microwave antenna design. I don't know if that has to do with really conductivity of the horn itself and how that interacts with the wave. But you're right, there is that kind of thing. And certainly in the case of acoustic waves, like ear horns, if I'd been deaf as I am 100 years ago, I would have held up a gigantic horn to my ear and tried to match the impedance of the sound waves in air to my eardrum or something, and also gather more energy, I guess. I don't know exactly how that works either. Yeah, no, good comments, Andy. I don't know. I really, it just surprises me because because I know you and I have talked about this, and flat earthers are well aware of this phenomenon. I mean, it's one of the places where they're just light years ahead of science, I think, in a phenomenon that they use to their advantage in kind of odd ways. But it really is interesting. It's very common, and I just think almost nobody. I've asked various AIs about it, try to find me a paper or somebody that's written about this, and they always end up being something which will talk about humidity effects on refraction, et cetera, but they never talk specifically about this thing, this tiny little narrow inverted image right at the horizon. Especially, I'm over water for sure, but maybe only because it's the only time we really get such a good approximation to flat. It's really about the flatness more than anything else. You just won't see this over any kind of a bumpy surface.
I'm not sure if this helps or not, but as you guys are talking, I've been doing some Googling here and there. And what it says is that the water molecules, as they evaporate, their molecular mass is less than the combination of O2 and N2, which is what we have in the atmosphere mostly. So oxygen and nitrogen gas. If you insert water molecules between them, the air would become immediately lighter.
Right.
And as a result, you would get a version of this. So it's not necessarily has to do with, well, of course, flatness plays a role, but I think if you have, let's say, a swimming pool and it's very steamy, like if you heat the water a little bit, then you probably would observe the same thing,
Right.
according to this at least.
Well, and that's why I say, I mean, I mentioned that before, that humid air is less dense than non-humid air, and that would cause this kind of a thing. It would cause light to travel faster near the surface. That's the condition you need for an inferior mirage. And that's why it's kind of my conjecture that that's what's going on. But I think, the problem with it is that, whenever you have that kind of a thing, there's some other dynamics going on in terms of that affects the temperature profile too, and temperature is important for determining index of refraction. It's all sorts of things. It's very convenient to just say, "Oh, that's humidity," and I'm kind of that's kind of what I do say. I mean, my best guess is that there's a little humid layer right above the surface of the water, but that wouldn't explain a basketball court thing. If I don't think I've seen it. Andy was talking about seeing it. Go ahead, Ben.
It just creates another problem. If that packet of humid air is lighter than the surrounding air, why doesn't it keep rising?
Well, presumably it would, but it would presumably also be, continuously replenished. Maybe, but once again, only if, I don't know. Only if what? Is it always the case that directly above water you've got kind of particularly humid air? I don't know. I can imagine that. I don't know that that's the case. Maybe, and it is convection. Winds. How important are winds?
I think it's
or
not simple if you think about the dynamic.
I don't think it is either.
You've got molecules of water escaping thermally from the surface. There's going to be a gravitational effect on those. There's going to be vapor pressure in the atmosphere trying to constrain it. There's going to be rising parcels of air because they're less dense. It's quite a complex little dynamic, I think. And in terms of what wins over, you've got the stuff Andy's talking about, boundary layers, surface friction with the water, there's always a prevailing wind at sea. So what is that doing to that mix of air molecules? So I don't think it's simple, is the short answer.
That's it. Well, I completely agree. That's why I say, I mean, my fundamental thing, I really like the humidity thing. I think the humidity, I'd be very surprised if humidity isn't central, but I just think it's a long ways from a satisfying explanation for all the reasons you said.
It's a bit like, for example, getting obsessed about Reynolds numbers when trying to work out why a full-size 747 doesn't go as far as
let's not go there. Maybe we can go there later in the after party.
Well, I was gonna say I have noticed in some of my photos, like where I'm up a few feet so that the horizon is, let's just say 3 miles away or something like that. and I zoom in to where that horizon is about in focus, and I got some photos where I have boats beyond that are partially hidden, and the surface of the water will look often wavy or peaky or something
Uh-huh.
like that. And part
Right.
of me is thinking like, oh, maybe I am focusing on waves because like I'm literally seeing a wave that's like 3 miles away. But often they don't really look like waves. They're a little too peaky.
Right.
And I think what's going on is you have these, it's the
It's
refraction
not uniform.
yeah, it's not uniform. It's a little
Yeah.
tiki and weird, and if you take video you will see they kind of dance around a bit.
Yep.
So you can imagine, once you have unstable air, it's going to start rising in columns, and then you're going to have areas of descending air, and so it's it's mucking around out there. There's action. So it is complicated.
Yeah.
I see that a lot. Like it looks straight until you zoom in, and then suddenly it's not that straight anymore. Um, so my solution to this, I've talked about this before, I still haven't done it, is my buoy test thing where I'm about halfway, maybe 3/4 the way to doing this. I have 5 buoys that I've made out of 2-liter Coke bottles, and I've actually already poured some. Well, I use mortar into them, into like 4 inches at the bottom, and I have these 4-foot dowels that I have to replace a couple because my dog got to some of them. And I so I had this idea that I'm gonna get these 5 buoys. I'm gonna get them all level. Like I can take a photo at the dock where they're perfectly level. I got a styrofoam balls to put on as targets, and then the idea is you stretch them out over a couple miles, and you're not looking at the bottom few inches. You're looking at 4 feet above the water, and you can compare that. And so you'll remove. I will if I if I ever do this. If I don't do it, then what I've done is really dumb. But so I have to do it. Um, um, but I'll be looking 4 feet above the water rather than 6 inches above the water. So my hope is that removes this effect.
Yeah. Let me, I was just reading some of the comments. I'm sorry I didn't, I think Wissam may have left, but I appreciate, oh no, Wissam's back. Okay, good. Yeah, thanks Wissam for exposing my shilling for Big Pool Noodle. Fun stuff going on there. Yeah, I've had a lot of people. In fact, if you look at the photos of me on floating on the lake, it looks a lot like Henry Fonda, because who was in the Golden Pond. For those of you who don't know, it's kind of that we were making on Golden Pond jokes all week. And Henry Fonda wears a bucket hat just like I do. My trademark, as you can see in my PTR, there is the bucket hat that I'm constantly wearing. So Henry Fonda and I were made for lakes on in Maine. Anyway, sorry. So I just wanted to comment on a couple of those. Thanks for all the fun stuff going on. Io wants me to do a future episode on warp bubbles via quantum vacuum fluctuation. I hope you're kidding, Io. You know I don't do stuff like that. Oh, he's not here. Good. Okay. Anyway, sorry. A little aside, just to catch up on the reading. And we've lost Benjamin, so I now call him Benjamin all the time. Steve Appel pronounces his name with an R, and I rather like that, so I've kind of taken to doing the same thing. Anyway, as you can see, I've got nothing more to say. Anybody else have anything more to say?
Well, I'm gonna sell my shares in pool
Big
noodle
pool.
stocks now that we've pumped it up. It's dump time. Let's go.
It's probably the case. Actually, I think I'm just gonna. If we can just get Trump to put some tariffs on pool noodles, we could probably milk that because it would only last until
We
the
both know
Maine
they
guys
come
got
from China. That's it. That's all you
that's
have to say. Say no more.
everything does. So
Who
that's
knows?
okay. So pool noodles out, I think. Any last words? Let me just. So Shamash, do you want to talk? You're approaching the end of your philosophy of science. Your 40 plus episodes on philosophy of science.
I mean, yeah, I the original plan was to give everybody a fair introduction to the issues in science. Not sure if I was successful or not, but that was the intention. And so maybe I'm not sure, 5, 6, 7 more rooms of this, and we move to doing something else. I'm guessing some ethics, some politics, some probably economic theory, an introduction. I'm open to that as well. We can do that. So yeah, I'm not sure. I would need to take a break, like
Yeah,
after we finish the science bit, because it was so intense for me every
it
week, every
is.
week. But yeah, it's not the end of Philosophy Wednesdays. The show is here to stay.
Well, let me
If you
put in
do
a
it,
vote for
sorry.
ethics. Yeah, go ahead, Ben.
And I was going to say, if you do economic theory, for Christ's sake, don't start from the standpoint that it's based on mathematics. That's where economists. That's why economists are all broke. Don't start from that point of view. Just make sure that you understand that mathematics is a tool, physics is the base connection with reality, then chemistry, then biology, then psychology, then economics. So you best base your economics on psychology. If you try and do what these pop economists do and try and make mathematical claims about the world, then just look at the car they're driving. That's all I'd say.
Where does sociology fit in there? Is it before or after psychology?
Oh, I don't know. Good question. Somewhere up there with the psychology economics thing. Probably. I don't. Probably. I don't know. Actually, that's a good. That's an open question where that sits in the stack. But for sure, psychology and um, economics sit on top of biology somewhere. So don't go straight to them. Don't pretend your economics is pinned on mathematics, because then not only will it be bullshit what you say, but it will also you'll end up broke if you follow those models.
And we've been joined by Arianis. Welcome, Arianis. I don't know if we've spoken before or not. Did you have comment or question?
Yeah, so I'd like to comment on whether or not the economic profession is reducible down to the sociological profession. I don't know if you have any comments on that.
Now, I don't know. I hesitate to say this, but you sound a little bit like the president of the United States. You're not Donald Trump, are you?
Who knows? Who knows? Maybe you might want to ask the Democrats that. Maybe there's Ariana's files, just the same way there's the Epstein files.
Okay. Well, yeah. Thanks for joining us, Mr. President. And kind of, if I could just put in a little request, just to like tamp down on the bullshit, maybe just a little bit less, be a lot happier. But thanks for joining us, David. You're here with us too. What have you?
Also, while you're at it, Mr. President, go and be one of the first narcissists in history to go and get some professional help with your condition, and leave office because you're not suitable mentally to hold that position. Just while you're at it.
Thanks,
Don't
Ben.
listen to
Good.
Fake
them.
news.
Don't
Fake
listen to
news.
them.
Everyone knows.
Go ahead, Arianis. Finish up, and then we'll go to David. I mean, sorry, Mr. President.
David can go. David can go.
All right, David. Go ahead.
Hard to think that missing Benjamin, we got something more challenging. But I was just going to say, I would put economics not in the hard sciences. It's definitely in the social sciences. It's about decision making, and Wissam should probably be part of that, the neuroscience, and just understanding maybe an economic history of economics, history of money, history of religion. I think those things kind of go hand in hand.
Okay, well, we're doing a little mini Philosophy Wednesday here on Friday, Shamash. How about that?
Yeah. Apparently people take care of it. I'm not. You know what? I need to ask you this question, John. I need to ask you this question. Why do you care about whether things are level or horizontal, or what problem does that solve for you? I mean, it doesn't matter, does it?
Now you're just directly ripping the piss out of me, which I love, by the way. So carry on.
Great, fantastic. That was the intention. So please go ahead.
Well, I do think it's really interesting because I have encountered people who I think literally think that you can prove that the Earth is flat using the meanings of words, and they'll claim that level means flat, and you can't have level without flat, and so therefore the it's literally the definitions of words that determine the shape of the planet Earth, which I think is really an interesting kind of way to go at things like that. So it's worth really
Well, it
examining
saves you
what
getting
that
out there
means.
and doing any actual experiments, though, because if you just
Yeah,
mess around with the definition of words, you can just sit in your armchair and try and win the argument.
that's right. Yeah. So anyway, that's why I know that was semi facetious, but but that's one reason. Okay, I don't mind. I don't mind closing this thing down. We can maybe do an after party like we often do. Those without Benjamin, I don't know how long that would last. You really have to have a whipping boy, somebody who's willing to put things out there that need to be whipped. But maybe he'll come back.
We can totally talk about Sabine Hossenfelder's last
Oh, right.
episode about those.
Oh, that's a good point. I watched it, but I didn't pay it close enough attention to really. And I think I kind of well anyway. Yeah, that's for the after party. But I do think you're right. We need to have a more discussion of that now
Yeah,
that
you'll
I've
you'll
watched
get
it.
him. He'll come. If you dangle
Yeah.
that room title for 5 minutes, he'll come.
I also, unfortunately, I have things I've got to do today, so I'm not going to start an after party myself, but maybe later on this afternoon, maybe there'll be another. Sorry, Shamaj, I guess that doesn't work very well for you and Ben, but anyway, if somebody wants to start an after party, that would be great. I don't think I will, although I might at least listen and chime in. Otherwise, I think I will start to shut this thing down here.
Who's
Thanks.
starting the after party? I'll go do that now. I will
Okay.
have to hand over to you, Shamesh, after a while, because we're going to watch Jaws, because we know all about the most recent and up-to-date movies. It is their 50th anniversary. I'll start an after party now, and if people want to find it in Scientific Discourse, then come and join us for more science and anything but philosophy.
Okay, good. Yeah, speaking of one of the things we had to watch while we were in Maine, apparently it's a tradition with the people I was with, is What About Bob? I don't know why exactly. I had seen that movie before. It's not Bill
There's
Murray's
a movie
best
called
movie.
What About Bob?
What About Bob? Yeah, oh,
Yeah.
yeah. Oh, anyway, well, so it's a Bill Murray movie, and I like The best movie ever made was Groundhog Day, so it's getting pretty close to the best movie ever made because it has the same guy in it. But that's maybe just my opinion, but it is my strongly held opinion.
It does have some of the best mentally ill volleyball.
I think sorry, just to go on a little bit, I think Groundhog Day is the perfect movie because it takes a great concept, milks it for everything it's got, and does it just enough. Milks every concept just enough. It is the perfectly constructed movie, in my considered opinion. I did see a movie. I will say yesterday I went to the movies and saw one that I will recommend to everybody called The Life of Chuck. Has anybody seen The Life of Chuck? It's pretty weird. It's a Stephen King short story brought to the screen. It's pretty good, pretty weird, but I like it. Light science fiction. Okay, now I really am going to shut this thing down, and we'll move over to Ben's after party.
I have the link in chat, so if you just copy and go there, if
All right.
you're interested in more messing around.
All right, very good. So thank you very much. I think we're going to end with another segment from the planets. This one, Jupiter. We started out with Mars. We're going to end with Jupiter, and we'll see you. Oh, no, that's right. Oh, right. And I have to point out that I will be in my summer camp in Mendocino next Friday. So yeah, it will not happen. I'll have to talk with Ben and see if he wants to do something, or Andy, maybe. If anybody wants to step up and, take the reins, let me know. Next Friday. Anyway, and the week after that probably will be tough too. So it might be a little dry spell, but we'll get back to it at some point. All right. Thanks everybody for coming, and see you next time, whenever that is.